Good morning, everyone. So Heinrich already introduced what we're talking about today, maximizing utilization. So why would we want to do that? We're going to talk about why we do this, a quick intro to the capacity planning process, which applies to any kind of capacity planning, and then we'll dig into what is utilization and where can you lose it. So LLM accelerators, so GPUs, have become extremely expensive and scarce across the whole industry. And, they cost a lot of money, they use a lot of power, they're very hard to get unless you have close friends in NVIDIA. In Google, we also have access to TPUs, which are another kind of accelerator, but these are also not an infinite resource. So in my team, in Workspace, we have to show that we're making good use of the accelerators that we have access to. Otherwise, it would make sense for someone else in Google to use them or to sell them, rent them to a customer. And if you run out of TPUs, if you run out of accelerators, then you start serving errors, as you can see. So what is capacity planning? It's basically making sure that you have enough compute resources available for the demand that is coming into the system. So demand here is users bringing requests. You can forecast the demand to some extent, and then you make sure that you have enough supply available. And that can be by buying more supply or buying accelerators or moving them around within your company or increasing how many you rent from someone else. And we break down demand into two types. Organic demand is sort of natural traffic growth, user engagement increasing. And inorganic demand is when we launch something new. We make a new feature, we add a call out in the UI that causes more people to use something. And then, the rough process is that you try and forecast this demand as best you can. You order more accelerators if you're running out, but then you have to allocate them. And what's particularly important here in the LLM world is that you have to allocate the accelerators to particular models. And you have to run a certain amount of chips, as we call them, for the model so that you have enough capacity for when the requests come. What gets interesting here is that we also monitor the utilization of these TPUs, the GPUs that we use. And we'll dig into that next. So all of our features are designed to limit the cost of the accelerator usage that they have. And that just so that we get the most bang for the buck for the accelerators that we have access to. You would want to measure essentially efficiency, which is how well are you utilizing this resource for the business value that you're getting out. But that's very hard to do because the business value is hard to measure itself. Like how much success, how much productivity the customer is getting is a sort of a lagging value to measure. What is fairly easy to measure is the utilization of the accelerator or of all your accelerators. And this is roughly the percentage of the time that the accelerator is busy so that you are putting work through it. And then, basically it is hot. And we measure the duty cycle, and that's our utilization metric. And we actually measure that at the 95th percentile across the week because there can be little spikes that don't really help with the overall measurement. It is worth noting that this is a limited metric. It has some shortcomings and it can cause you to do weird things if you take it too seriously. Like doing work that you don't need to do to keep the number up. And that's just the start. But it's worthwhile to have this because at least you can see in your company, in your organization, are the accelerators being utilized. So we started off on this journey without really knowing what our utilization was. And then when we started to measure it, we saw that it was low and we were under pressure to make it better. And at first we were sort of scrambling around, trying different things. And then we came up with a model where we characterize our reduction from a sort of theoretical 100% as different kinds of losses. And these losses then become engineering projects that we can work on to make things better. And each of these is interesting and can be tackled separately. And as you fix problems for these different kinds of losses, you will increase your utilization and eventually get back up to some reasonable number, which won't be 100% because there's, as you'll see, each of these can only be improved. It can't be eliminated entirely. So we'll look at 5 of these, and then we'll talk about what you can do. The first loss type is max utilization. So for each of the large language models that we run, they can't actually be run at 100%. Even if you just had, a perfect setup, a perfect model, perfect set of chips, you can't run them at 100%. You start seeing errors before you hit 100%. And this is different for different models that we've run. And there are things you can do to improve it, but there is still some loss at the top. So it's sort of a ceiling that you run. Ways to improve this are load testing, sort of old school, but actually it's come back into fashion. Tricky part here is to get representative traffic to load test with, because if you start with synthetic traffic, you end up load testing the synthetic traffic, and then what you get in production is quite different, and your load test is no longer valid. So ideally, you use some sort of sampled traffic, but that also can have difficulties with compliance or customer issues as well. Ideally, you get this load testing into your CI/CD process, like the previous speaker was telling us about, so that as you deploy new models, new features, you discover early whether you're having a regression before it costs you a lot of money. And you can also maybe use something called a redline canary, where you have one set of jobs that are deliberately running hotter to detect problems early. So one of the biggest areas for loss is actually what we called unmaterialized demand, which sounds fancy, but it's because in our process, we estimate the demand in the capacity planning process. We estimate the demand. We say, okay, we're launching a new feature next week. Let's scale up our set of accelerators for this product. If that feature is late, if it doesn't come next week, those chips are now allocated and not doing anything useful. And that can end up actually costing you a lot of money. And that traffic ramp up may, even when it comes, may be slow or maybe less than you expected. So that was one of the areas where we had to get a lot more rigor into the system. First thing we did was to use some of this capacity for other things. So if you have unlaunched capacity, then make it available for doing offline workloads or training, evaluations, that kind of thing. And you can pool it between groups. So if you have different groups in your company that are all building AI features, you don't all need to have a buffer that you're sitting on. You can share the buffer for the unlaunched features, and that helps a bit. The other thing you can do is realize that your launches typically don't come on the day that they say they will. And you can also turn it, instead of saying, we'll give you all of the accelerators up front, we'll say you get 10% to start and then ramp and then see. Because also sometimes you launch and it turns out that the feature is not as expensive as you predicted based on your synthetic load test, and then you're still losing more there. Another loss type that we've been working on is redundancy. So all good SREs know about N+1, where you provision at N+1 redundancy so that you can lose your largest cluster in an incident. This is sort of a article of faith for SREs. You must do this. You will always be N+1, maybe N+2. When you're dealing with these accelerators, some of that comes into question. Because they're such an expensive and constrained resource, you may have to revisit that assumption. Things that we've tried here is to have more small clusters so that then the extra cluster that you're provisioning is smaller than if you just had 3, for example. If you have 5, 7, 9, the last one is not as big as it would be. You can also adjust the redundancy requirements for different workloads. So if you have some features that are interactive and some features that are more like a pre-generation or sort of a nice-to-have feature, you could adjust the deployment of the accelerators for those to be different. And maybe a hint is that regionalization, where you have to have an EU version and a US version, makes this even more painful. So that's also something where you want to keep the redundancy under control. Quickly on disaggregation mismatch. This is a kind of serving in LLMs where you can scale the prefill and decode phases separately. Very interesting. I won't explain it all here, but this ratio is something that you need to adjust over time, potentially with new models and also with changes in your traffic mix in production. And you can be losing quite a lot of basically accelerators with a wrong ratio running. This is painful to do because you have to often redeploy the model, test, run a load test, push it to prod, see that it doesn't work as beautifully as you hoped, and repeat. And the last of these losses, and I think the most significant and the one where I've spent most of my time, is what we call fragmentation loss. So you have to understand that when you serve an LLM, it has a certain minimum footprint that you need to serve it. So, where you can run some models at home with one GPU, but for the really large models, you need, dozens or hundreds of GPUs. And the bigger the model, the bigger the minimum footprint. Because of this minimum footprint, if you say you need 100 GPUs to run a model, if you don't have enough queries coming in to saturate those GPUs, you are losing utilization on those remaining GPUs. So say you need to, in order to saturate those 100 GPUs, you need 10 QPS. If you only get one, then there's 9 QPS worth of accelerators lying on the floor. What that means is that larger deployments or larger shared deployments make more sense than a lot of isolated per product, per feature deployments. And this is counterintuitive to SREs because we've got the idea that more isolation is better. But in this LLM world, you lose a lot by having isolated deployments. So an example, we have Gmail and chat using separate deployments of the same model. So the same physical model is running in 2 sets of GPUs for isolation reasons, but neither can fully utilize them. And the leftover chips in each of those deployments are essentially wasted. So if we can get them to use the same deployment, then we save. That is easy to say in theory, but in practice it can be tricky because it may not be the same model. It may be a fine-tuned model that has different properties or different sort of performance characteristics that they rely on. And so working through that to limit the number of models, limit the number of deployments was what we did to bring all of this fragmentation into larger clumps and eventually a single instance of the model. Something that you can look into for this is LoRa. So low rank adapters can be helpful here because you can have one large model and then a couple of LoRa adapters on top so that you can still get some of the aspects of fine tuning that you need. We also found that the recent generations of model are good enough that you often don't need fine tuning and you can go a long way with prompt engineering. And I think for most teams, I would probably suggest prompt engineering first. So that's how we've done it so far. But each of those loss types that we talked through was quite a lot of work to do. And you saw that some of them had to be done multiple times or had an iteration loop in them where you have to keep actuating production. And this was being done by hand to start with, and then with spreadsheets and with some scripting and some tools. But it was starting to become a real drag on the SRE team. So what we have moved towards now is capacity automation. So the same flowchart that we had at the start, we now turned from a human toil machine into automation. And we instrumented the inference that we do of the LLMs to report how many TPU tokens per second are being used for different features and different products. And we capture all of that. And we use that to forecast the demand from week to week. So the organic demand is forecasted, projected out, whatever way the little growth slope is going. And we also keep track of what launches are coming up and how much we estimate those to be. So then adding those together, you can say, okay, for this product, next week, it's going to need this many accelerators. And then you can allocate those. And like we said, you might do it not in one big block, but you might stepwise increase the number of accelerators available to them. We can even take this further and actually instrument what we call experiments, which are feature flags. And you can watch as the feature is being turned on by the developers, to 1% or to the first small group of users, you can see how much is it costing. And then you know that the next ramp is not going to be for another day or two. You can extrapolate the cost for the QPS that you expect to come and use that to get an even more fine-grained estimate of demand. Especially useful here is once you do automation, you can run this process more frequently. Instead of doing it weekly, you can do it daily or 2 times a day. And then as you tighten up that loop, you have less chips lying around because you're moving to more of a just-in-time process. Finally, we also started to look into auto-scaling. So this is like medium-term planning for like the next week of demand. You can also have auto-scaling that will adjust your ceiling almost in real time if you're dealing with spiky traffic. So what did I want to teach you today? We talked about capacity planning, utilization as a metric, and how you can lose utilization. So the loss model as a way of turning a problem into a series of engineering projects. I suggest accelerating the capacity planning cycle to reduce the stranded accelerators that you have, and automation becomes necessary at a certain scale. The biggest takeaway is limit the number of different models and separate deployments of them as much as possible, especially as your AI features grow. This is where you will lose the most amount of resources. Thank you very much.